this is Douglas Rumbaugh, and in this video I would like to introduce a very handy, very useful data structure called a binary heap. We're going to begin with a motivating example. Here's a problem. We want to find the smallest element in a list, and for our purposes right now, let's assume a list consists of unique positive integers. This is going to make life much simpler. It doesn't have to be that way, but we're going to do that for simplicity. So here is our data, and our goal is to find the smallest element. Now, when faced with a problem like this, there are two different solution approaches that you might take, very broadly speaking. There is what I like to call the algorithmic approach and what I like to call the structural approach. Now, particularly if you have not been formally trained in computer science, very good odds that your default stance is going to be an algorithmic approach. So let's take a look at that first. The simplest and one of the only algorithmic approaches to this problem is just to scan the list for the smallest element using a slight modification on what's called a linear search. So we simply look at the data, we keep track of what the smallest thing we've seen so far has been, and we walk down the numbers. Once we've walked down all the numbers, we can see that the smallest thing that we have seen so far, after looking at everything, is 0. That is the algorithmic approach. Now, this specific approach, begins to have problems if we want to generalize the problem just a little bit. So what if, rather than finding the smallest, I wanted to find the second smallest, or the third smallest? Or, very similarly, what if I wanted the 5 smallest? You can see how these are all variations on the same theme, but if we wanted to make our linear search approach work in that case, we are going to have to tack a lot of extra complexity onto it, and it's going to become increasingly difficult to manage. So, rather than that algorithmic approach, let's instead look at a structural approach. The question is, can we reorganize the data in a way that answers the question that we want? Can we facilitate answering our question by changing the way the data is organized? For this specific situation, what that means is we want to impose an ordering on the data. We want to impose an ordering such that we can find the minimal however many values there are. Now, if you think about it for a second, probably the first thing that's going to come to your mind is, why don't we just sort it? And so we can end up with something like this. This is the same data. These are the numbers, the values in the array, sorted. And then these are the indexes into the array. I'm starting at 1 for simplicity here. And so as you can see, what we've done is we've effectively assigned each value a number, and that number corresponds to where it falls in the ordering. So the smallest number gets 1, and the biggest number gets 15. If I want the 5 smallest numbers, I just read 1, 2, 3, 4, 5, and there they are. This is sorting. And what we've effectively done is used an array and modified the data such that the array index corresponds to the order that we want. Now the thing is, that's a very strong ordering property that we've established there. And as a result, it's relatively expensive to get to. And we've actually, if you think about it, we've done a lot of work that we don't actually need to do. So for example, if I want just the first 5 numbers, I don't care about everything down here. But when you're sorting the array, you kind of have to sort all of it. So we've spent a bunch of extra work sorting data that we don't actually need to sort. Is it possible that we can come up with a weaker ordering principle that will allow us to answer the question while perhaps doing a little bit less work? And the answer is, of course, yes, we can. And we're going to use something called a heap to do that. The basic idea is this. Here is our data, and we are going to take that data and insert it all into a structure that is known as a heap. So this process is going to reorganize the data in a way that is helpful to us. Once we have the data inserted into the heap will allow us to ask, what is the biggest or smallest? As you can see, whether we're looking at the biggest number or the smallest number, the problem's the same. What's the smallest number that's inside of you? And so we can take that and remove it. So we get 0, that's the first smallest. And then we can do it again. pull out the next smallest number and the next smallest number and so on. And so what you see here is that assuming we can construct this heap structure somehow in a reasonable amount of time, we can do less work because we pull the numbers out in sorted order, but we don't actually care necessarily how they're arranged inside the heap so long as this property of removing them in sorted order matters. And we're only doing a bunch of work to remove the numbers that we want, not all of them. So then, before I get into how to build a heap and all that, let's take a look at this in action. So I've gone ahead and implemented a min heap, a heap that has the property of removing the smallest number. And we're going to look at that code in a short while, but first let's actually use it to do something. So let's just solve that problem. I have a program here which accepts a command line argument k and prints the k smallest elements from this array. We need to actually implement this. And this is in the C programming language. There's not a whole lot of C-isms going on in here though, so don't worry too much about it if you're not familiar with C. You can follow along in whatever language you like. The core principles are the same. First thing we have to do, per our little diagram from before, is we have to construct the heap. And so I'm just going to go ahead and do that. I have a function that I use to build a heap of a specified size. We'll talk about that when we get there. And then once I have the heap, I need to insert all of my data into it. Just like that. So this is accomplishing the process of building the heap. We don't know what's going on inside of here, but what matters is that if I then do this, if I then remove those elements from the heap, they come out in the correct order. The reason why I'm setting this up this way, where I create a variable and then I pass a reference to that variable in, is my remove heap function accepts basically a buffer and puts the value in that buffer, as opposed to just returning it, because I'm using the return code to determine whether it worked or not. And then of course we can't forget that we have to destroy the heap when we're done, because C is a manual memory managed language, so it won't do that for us. So this is an example of using this heap structure to answer that very question. We are going to load all the data into the heap, and then we are going to remove from the heap k elements, where k is the number of elements that I want in sorted order. So let's go ahead and give this guy a shot. So if I say 1, that should give me the first smallest element. And if I say 3, that should give me the first 3. If I say 9, there are 9 elements in the array total. That should give me the array in sorted order. And you can see this, in fact, is doing what it's supposed to do. And here's the array. So you can see we are actually getting the correct numbers in the correct order. Okay, so that's how a heap is going to work. Now what remains is, of course, the question of how do we make one? So a heap is going to be built on a data structure called a tree, which you are probably familiar with. Specifically, a heap is defined as any tree that satisfies something called the heap property. I find this a very satisfying definition because it says that a heap is a heap. But if we define heap properties, it'll actually be a little bit useful, so let's do that. The heap property states that every vertex or node in the tree is going to be smaller or larger, in the case of a max heap, than its children. I find that pictures are worth 1,000 words, so here's what one of these things looks like. You will note that each of these circles represents a vertex in the tree. The arrows represent parent-child relationship, so 5 is the parent of 7 and 8. And you can see that my heap property is satisfied. For each node, the children of that node are less than it. So 5 is less than 7 and 8, 7 is less than 10 and 9, etc. You'll also note this is a binary tree. Each node has at most 2 children, and that's going to become important for our representation. So it's actually more than just a binary tree. It's what's known as a complete binary tree, which is rather important for our implementation of this thing. Now, a complete binary tree it's a binary tree, but it's a binary tree where there is a restriction on where you stick new nodes. Basically, if I wanted to add a new node to this tree, I have to do it at the lowest level of the tree, starting from the left and moving right. So I'd have to stick a node here, and then here, and then here, and then here. That's very important because it ensures that the tree remains balanced. That is to say that the maximum height difference from the deepest node to the shallowest node remains no greater than 1. You can imagine a case where if I take my tree and I just insert nodes like this, 5 left child, 7 left child, 10 left child, left child, left child, left child, I wind up with a very unbalanced tree. In fact, it approaches a linked list in the worst case. This balancing property keeps the height of the tree under control, which is important because, as we'll see, the height of the tree is what governs the efficiency of the operations we're going to be performing on it. The shallower the tree, the better the performance. Just as an example then, if I wanted to insert the number 18, I could not do it here. I have to do it here because that is this complete binary tree property. Now, what's cool about the complete binary tree, in addition to being balanced, is it lends itself to a very convenient array-based representation, which we are going to use. You noticed I had to specify how big the tree was in the program we just wrote. This is why, because I'm using an array as the underlying data structure. So if I number the nodes on the order in which they're inserted, so 1, 2, 3, 4, 5, 6, 7, etc., etc., if you look at it for a little bit, you might notice a very special relationship between these numbers. Specifically, for each vertex k, where k is this index number, not the value of the vertex, but the actual index here, its left child is going to be at index 2k, and its right child at index 2k plus 1. So see 1, and then 2k is 7, 2k plus 1 is 3. Likewise, say here for 3, 2k gives us 6, 2k plus 1 gives us 7. So you can see we have this very nice property. And we can then use the index of the values in an array to represent where they are in the tree. Very convenient. But that only really works in the context of a complete binary tree, because otherwise we then have to account for, say, null values, right? Because if I had this number 18 here, there'd be 2 valid vertices right here that aren't populated, and I need some way to skip them. However, if I do it this way, in the complete binary tree way, the number of elements inside of the tree also gives me the array index of the last element. Any array index greater than the number of vertices, if we're starting from 1, is going to be invalid. There's nothing there. So it makes managing this array very convenient. Okay, so this is just explicitly showing that this is our array, index 1, 2, 3, and so on, and these are the vertices packed into the array. Now you may then be wondering something, which is if we are using a complete binary tree, which places a restriction on where we are allowed to stick things, we have to stick the next vertex right here. How is it that we could possibly maintain this heap property as we insert nodes into the tree? Right, because say I wanted to insert the number 2. Well, we know that the number 2 is basically going to have to go here, and we're going to have to rearrange some things to make that work, because 2 is going to be the smallest thing in the heap. So how can we do that? And this is actually really handy too, because if we can figure out insertion like this and get that working properly, that gets us building the object initially for free, because we just insert each element one at a time, and then the heap will build itself out. How do we preserve this heap property? Well, let's insert 2. We must stick the 2 here. The problem is that that violates the heap property, because 2 is less than 10. What if we just switch them, right? Swap 2 and 10. That fixes 10. However, you'll note we've now broken 7, so let's swap it again. And swap it again. And look at that. Our heap property is maintained. And this is our insert procedure. We're going to take the node and stick it in the spot where we're allowed to stick it per the complete binary tree property. And then we simply move it up the tree until the heap property is satisfied. Just like that. This process of shifting vertices up the tree is what's called upheap, because we're moving it up the heap. And that gives us our insert algorithm. We stick a new vertex into the leftmost open spot at the bottom of the tree. which is going to be given specifically by the number of nodes in the tree, right? We use the number of nodes in the tree as the index into our array, and we stick it there. And then we swap the vertex and its parent until the vertex is larger than the parent. And note, in the worst case, we are going to run in logarithmic time, because the worst case scenario, which is actually this scenario right here, is we swap it all the way up to the root of the tree. And the tree, if it's balanced, which it will be, is going to be of logarithmic height. So at most we have logarithmic swaps, and so our worst case scenario for insert is logarithmic, which is pretty good. So how about removing the root element? If I want to remove the smallest element, well, we have to replace it with something, right? I can't just take the root away, because then I have two trees and not one, so I have to replace it with something. The problem is that I can't just replace it with anything, again, because of the way we are representing this as an array. If I wanted to actually take the 5 and put it here, I would then have to take the 7 and the 9 and relocate them within the array as well. If I want to take a node and put it at the root and not have to restructure the tree and preserve this complete binary tree property, again, there's only one option. I have to take the bottom leftmost node, in this case 10. So let's go ahead and plop that 10 up there. And as you can see, the structure of the tree is preserved, but the heap property is not. We have the same problem we had with insert, just in reverse. Now 10 is bigger than its children. So how can we handle this? Well, we just swap it, right? Just like we swapped up the tree for inserts, we're going to swap down the tree for deletes. So 10 is going to swap with 5 like this. Now you may ask a question. Why did I swap with 5 and not 8? Is there some rule about swapping? And the answer is there is. We're always going to have to swap with the smallest child vertex. And this is to ensure we don't create any new heap property violations. So if we go back to the situation where we have 10 here, it needs to swap down one more time. And I can swap with the left child 7 or the right child 9. Now 7 is less than 9, so by the rule I just stated, we would want to swap 10 and 7. What happens if we swap it with 9 though? Let's break the rule. Notice what's happened. 10 is now happy, but I've created a new heap property violation right here because 9 is larger than 7. So what I have to do instead is swap it with 7. And if I do that, everyone's happy. The 7 is still happy because it's larger than both its children, and the 10 is now happy because it is, well, it has no children, so it satisfies the property as well. And this gives us our remove. This process of shifting down is called down heap incidentally, just like up heap for the other one. And this is our remove root algorithm. We're going to remove the root vertex, replace it with the last vertex in the tree, and then repeatedly swap the vertex with its children going down the tree until it is smaller than all of its children or it becomes a leaf. Just like with the insert algorithm, this is at most going to run in log n, where n is the number of elements inside of our heap, because again, worst case scenario is we move from the root all the way back down to the bottom of the tree, which is logarithmic because our tree is balanced. And so that gives us our two primary operations that we care about on the heap, putting things into it and pulling things out. And you'll see that we are maintaining this ordering property that we care about, but only with respect to one element in the tree, only with respect to the root. The rest of this stuff, as you can see, is in no particular order. This means that we can have this efficient remove the smallest or largest element. It's going to hurt us in other situations though. So for example, compared to a binary search tree, which you may be familiar with, I cannot efficiently find arbitrary values inside this tree. Right? The heap property does not give me enough information to efficiently search for specific things aside from the root. I'd have to look at the whole thing. So searching is not as efficient. But it can of course be done, and so there are a variety of other operations you might perform on a heap. You can search for an arbitrary element, you can delete an arbitrary element, which is of course going to require restructuring. With up heap and down heap, you can do that. So I'm going to not talk about that anymore. Modify an element value, same problem. You will have to reorganize the tree, so up heap, down heap. With those two operations, you know enough to do most anything you would need to with with a heap, and I will leave it as an exercise to you to figure those things out if you're interested. So we're not going to talk anymore about those. But let's take a look at some code implementing the insert and remove operations that we just discussed. So this is the interface for my min heap that I created for this video. But incidentally, the link to this code it's up on GitHub. The link is in the video description if you would like to download it and tinker with it yourself. We have the ability to create a heap. This size gives the size of that backing array that we're storing the values in. We can destroy the heap when we're done. Again, C is manually memory managed, so we have to do that ourselves. And we can insert and remove elements from the heap. And then, which we've actually seen these two in operation already, right? And then this last guy, check heap, is just a simple helper function for testing purposes that verifies that the heap property is maintained. So it checks every node and verifies that the children are larger than the node in question. So we take a look at the code. The first problem we encounter when attempting to implement the heap in C is that if we look at my definition of the array representation here, you'll notice that I started at 1. And so we have 2k and 2k plus 1 when the first array index is at 1. If we're using C, of course, we have to start at 0 instead, which changes the math a little bit. So these are the necessary relations to calculate the left child, right child, and parent of a given node based on its array index. 2x plus 1 gets you the left, 2x plus 2 gets you the right, and x minus 1 over 2 gets you the parent. So I define those as some macros up front for implementation convenience. The heap itself, representationally, is quite simple. I just track the size of the heap maximum, the number of nodes that are currently inside of the heap, and then this is the array of data. So this is my backing array. For no particular reason, I've used size t as the data type for this heap, so it stores unsigned longs. But you can, of course, change that data type to whatever you'd like, as long as it's fixed size. If you want variable size, things get a little bit more complicated. We're not going to get into that. So for the actual creation, you can think of this as being the constructor if you're more familiar with an object-oriented language like, say, Python or Java or C++, something like that. And this function has two goals. The first thing is it allocates the memory, because remember, C is a manual memory managed language, so this malloc function allocates memory. And then it also initializes the values. So we start the max out with size, because that's how big it is, and starts at 0 because it's empty. This is allocating the array, which is enough space to hold size number of whatever the data type is. And then these if not heap and if not heap data checks are just verifying that the memory was allocated successfully and returning null if it wasn't. Destroy heap just frees the allocated memory. So in C, every malloc call should have an associated free call to ensure that the memory is released and available for use. Otherwise, you have a memory leak. That's enough sort of C logistical details, though. Let's take a look at the actual insert and remove operations. So just as a check, which we didn't mention in the algorithm and structural definitions we just did, I verify that we actually have space to put a new node, and if we don't, right? The array fills up. And then all I do is, this is sticking the node in the leftmost open spot. As I mentioned, the size of, or the number of elements in the array just gives us where we stick the thing. So the new index is basically n, and then I increase it by 1 because we're adding something. And then this is the upheap operation. So for our node, while we're not the root, because of course the root can't move up the tree, and our parent is bigger than we are going to swap with our parent, and then our index becomes what our parent's index had been. This is that upheap operation, rolling up the heap until we're done. And then once that's done, we're inserted, and so we simply return 1 for success and move on with our lives. Remove is pretty much the same thing, just in reverse. Again, we have a check. If the heap is empty, we can't remove anything from it, so 0 for failure. Otherwise, go ahead. This is taking the current value at the root and sticking it inside of that input buffer where we're storing the result. That's how we get the result out of the function. Then we swap the root node with the lower left, decrementing the number of nodes as well because we've removed something. Note that this technically does copy the root value down to the end of the tree, but because it's in a vertex, or it's in an array index rather, that is now larger than n, or more specifically equal to n, it will never be seen, and then on our next insert it will get overwritten, so that's fine. Then we're starting at the node we swapped up and are going to heap down, or down heap rather, is at the root, so it starts at 0, and then it's just the same processes. While we actually have children, this min_child function calculates the minimum child and will return -1 if we don't have any children, so if we're a leaf. So we figure out the smallest child, and then if we are larger than the smallest child, we have to swing down the tree. And note, I'm only checking one of the children. I only have to check the smallest child for this to work. If you think about it for a little bit, you might be able to determine precisely why that is, but it simplifies the code quite a bit. So I swap down and then make the index, make my current index equal to the child because I just swapped places with it. And once that stops running, we return 1 because we are done. Let's take a look at this min_child. This actually covers quite a bit of ugliness relating to the implementation and edge cases, because we need to verify A, that I actually have children, as well as compare them. So it's fairly straightforward, if a little bit ugly. This, I calculate the left and the right index, placing a -1 there if I don't have a child at that point. And basically the child node exists if it's less than the number of nodes in the heap. Because remember, the number of nodes in the heap, this n, is what gives us the end point. That's our insert point, basically. So if it's less than the insert point, it's in the tree. If it's greater, it's not. And then if neither left nor right exist, then I don't have any children at all. If the right exists but not the left, then by definition the right is the smallest. If the right doesn't exist but the left does, the left is the smallest. And if they both exist, I have to do a comparison and return whichever one is the smallest. So that's the min_child. That's kind of the ugliest part of this. And then finally, I'll just mention check heap. This is the one that verifies that we are in fact a heap. So I'm going to iterate over every single node inside of our tree. And if the parent is larger than the node, then we violate the min_heap property, and so I return false. Otherwise, if we get to the end and didn't return false, then that means that the heap property is satisfied for every node, and we return true. So that is a perhaps not so quick introduction to the concept of a heap. It's a very useful data structure, and it may not seem that way, but if we flip on back here and we go back up to the problem that we're trying to solve, which is a little more generally find, say, the kth smallest element in a list, that actually summarizes quite a few different types of problem. So not only are we looking at finding the elements, finding like the kth smallest, but we can use it for sorting. As we saw, if I run my query program and I give it 9, the length of the array, that just sorts it for free. So using a heap, we can sort. That's incidentally what's called a heap sort algorithm, and it is one of the nice n log n time complexity sorts. It's not as fast usually as merge sort or quick sort, but as you can see, if you have the heap structure, you basically get the sorting algorithm for free, which is kind of neat. Additionally, it's used for a thing called a priority queue, which you may have heard of. You want to pull the elements out in order of priority. So if the priority is just a number, then you can minimize or maximize the number based on the heap property, right? And so you get a priority queue. Heaps are also useful for merging multiple sorted arrays together. So if you have like 5 or 10 sorted arrays and you want to merge them into one, you have to find what's the smallest element in all 10 of those arrays, put it in a new one. Well, easiest way to do that is just take the head of like the first element in every array, push it into a heap, pull from the heap, and then pull the next element from the array that that element belonged to, push it into the heap, and repeat until all of the arrays are empty. So you get a fairly efficient array merge using heaps as well. Quite a handy data structure, not super complicated, and something that, unless you have formal training in computer science, you may have missed. Algorithm or data structures classes rather really like talking about heaps in computer science programs, but if you're a self-taught programmer, you may not have heard of it. So there you go. I hope that you found this video interesting as always, and I'll see you in the next one.